Welcome to this lecture series in coordinate geometry. In this lecture, we'll look at the equation of a pair of straight lines passing through the origin and how to decide if a given equation is indeed that of a pair of straight lines passing through the origin. So let's recall some things that we need to know. So we will need to know about the zero set. So if we have some algebraic expression, then the zero set of this algebraic expression is the set of all the points a comma b on the plane for which f of a comma b is equal to 0. So that's the zero set of an algebraic expression. We saw examples. For instance, if we have this as our algebraic expression, then its zero set is a straight line of slope minus 2 by, this is a y. So the zero set of this is a straight line whose slope is minus 2 by 3, etc., etc. Okay, zero set of a product. So suppose we are given two algebraic expressions, fx comma y and gx comma y. Then we can multiply them to get another algebraic expression. And let me write this in a different color. So if f and g are algebraic expressions, then their product is also an algebraic expression. And their zero set, the zero set of the product is the union of the zero sets of f and g. Right? This is a very simple fact. And we need to know about quadratic equations. So if we have been given this kind of expression where a is non-zero, then such an equation is called a quadratic equation. There is a formula for its roots. Let me just write it down. I'm sure you already know. So these are the two roots of this quadratic equation. The roots can be real or imaginary depending on the value of b square minus 4ac, which is called the discriminant of this expression. All right, so let's not spend any more time here and move on. So suppose we are given two lines, L1 and L2. So here is L1, this is L2, and we have drawn them here. The equation for L1 is this and for L2 is this. So we are assuming that not both of A1 and B1 are 0 and not both of A2 and B2 are 0. One of these can be 0 and one of these can be 0, but not both. So we have these two lines which both of them pass through the origin. So one can express the union of these two lines as the zero set of the product of these two expressions, as we just recalled. So this, both of these lines are quote unquote captured by which equation? This equation. So this equation simultaneously captures both lines. In other words, the zero set of this algebraic expression is the union of these two lines. All right, so this captures a pair of straight lines passing through the origin. So we can expand this out and get so the equation of a pair of straight lines passing through the origin is of this form. Generally, it is of this form. We will prove everything properly. But as of now, we can see it is of this form, meaning it looks like this. One can write it like this. Some constant a times x square times, customarily we have 2h multiplied with xy and by square. So such a thing is generally speaking, and when I say general, I don't mean always, typically such a thing is a pair of straight lines passing through the origin. So the point of this lecture is to properly understand what is the expression of a pair of straight lines, or what is the equation of a pair of straight lines passing through the origin in full generality. What's the best we can say? Okay, so towards that we have this theorem. So suppose we have real numbers a, h and b, not all of them are 0. So some of them can be 0, but not all. Then this expression is the equation of a pair of distinct straight lines. Let me underline distinct straight lines passing through the origin, if and only if this thing, this expression h square minus ab, is positive. And before I continue, let me just say that the positivity of this is equivalent to the positivity of this expression. So all I'm saying is that this is equivalent to that. So if this happens, then this is the equation of a pair of straight lines passing through the origin. And conversely, if this is the equation of a pair of straight lines passing through the origin, distinct straight lines, not just straight lines, but distinct straight lines passing through the origin, then this happens. So it's an if and only if statement. Okay. So there are two directions to it. Let's do one of them and the other one would automatically follow out of this. I will maybe give a little bit of a comment as to how to go in the reverse direction. We will see, but let's first prove the less trivial direction. So we assume that this thing is the equation of a pair of distinct straight lines passing through the origin. Okay, so we want to prove that. Right, this is what we want to do. Okay, so there are two cases. These two cases are just to kind of facilitate a simpler proof. So case 1 is that one of these lines is vertical. So one of the lines out of the two straight lines that this equation captures, one of them is vertical, meaning one of them is the equation x equals 0. So assume one of the lines, both cannot be vertical because these are distinct lines. So assume one of the lines is vertical, which is to say that it is equal to x equals 0 or captured by x equals 0. Okay, so before we proceed, let's call this something. Let's call this expression f of x comma y. Okay, so therefore, since one of the lines is x equals 0, we have setting x equals 0 in this expression should give us something that is identically 0, should yield 0 for all y. Let me explain that a little bit. So what we have is, out of the two lines, and maybe let's say the two lines look like this, one of the lines is this. So every point of this line is in the 0 set of this expression, and every point of that line is in the 0 set of this expression. And precisely these points are in the 0 sets, nothing outside it. That's what it means to say that this is the equation of these two lines. So in particular, every point on this line is in the 0 set of this equation, and hence if you put anything, let's say a comma 0, you get 0 for all a, which is what am I writing? What I mean to say is, an arbitrary point of any arbitrary point on this line looks like 0 comma b. And if you substitute 0 comma b in place of x and y, meaning in place of x you write 0, in place of y you write b, this expression should become 0 because this point is in the 0 set of this expression. But this is true for all b, and hence all this is saying is that if you substitute x equals 0, then you should get 0 for all y. So this expression becomes identically 0. Okay, so all we are saying is that therefore we get by square equals 0. Right? For all y. For all real y. And hence b is equal to 0. Right? Therefore b is 0 and hence fxy is nothing but, so this is fxy because b is 0, which is equal to x times ax plus 2hy. Okay. So now we see that, of course, x equals 0 is in the 0 set as evident from it. I mean, we assumed that is the case, so not a surprise. And now, if suppose this were 0, if h were 0, then fxy would become x times ax, which is ax square. And hence, the 0 set of fxy would be precisely the vertical line, and hence the 0 set of fxy wouldn't be a pair of two distinct straight lines passing through the origin. It would only be one straight line passing through the origin. So therefore we conclude that h cannot be 0, because if h were 0, we wouldn't get two distinct straight lines passing through the origin, contrary to the hypothesis that this is the equation of a pair of two distinct straight lines passing through the origin. So h is non-zero. I don't want to write it. I have argued it. So I'll just say note that h is not 0. Okay. And therefore, what you have is this expression. I mean, fxy is therefore this. So thus, yeah, now we don't need to care about fxy. H square minus ab is equal to just h square because b is 0. But h is non-zero, therefore h square is positive. And we have shown that h square minus b is positive. So in this case, we are able to argue. So in the other case, we will assume that none of the lines are vertical. Maybe that should be done on a separate page. So case 2. None of the two lines is vertical. So then b is non-zero. Because as we saw, as soon as b is 0, x equals 0 would be a solution to, x equals to 0 would identically make our algebraic expression 0, and hence the vertical line would be one of the lines. So b is non-zero. And now say m1 and m2 are the slopes of the two lines. Okay. So then, setting y as mix for I equals 1 and 2 should make this identically 0. Again, what is going on? We have this algebraic expression whose 0 set is precisely the union of these two lines. The slope of the first line is m1, so it is y equals m1x, and the second line is y equals m2x. And m1 and m2 are both real numbers because none of these lines is vertical. Okay. So since this line, every point of this line is in the 0 set of f, setting, substituting any point of this line into this expression should yield 0. In particular, suppose you feed in the point a comma m1a. Pick a real number a, then this point is on this line. And if you substitute in place of x a and in place of y m1a, you should get 0. But you should get 0 for all a, and therefore this statement that we have written is sanctioned. just writing mix in place of y should make this expression identically 0. Alright, so what we have is ax squared plus 2hx mix plus b mix square is 0 for all x. For all real x, I mean, which implies, let me write it this way. So this is mi square, or maybe let me take out x square out. A plus 2h mi plus bmi square equals 0. This is for all x. And hence, this multiplicand should be 0. Right? This is just a number. This thing is just a number multiplied by x square is 0 for all x. So this number must be 0. So let me just write it in this way. And this is for both both these. This is true for both m1 and m2, and same for this and same for this. So I should have written for I equals 1 and 2. Same here and same above, but above there is no space. Okay. So just look at this for the moment. Oops, sorry. Yeah. So looking at that, we see, so this is the punchline actually. So therefore, m1 and m2 are two distinct roots, distinct real roots of this equation. So what I'm saying is, think of m as a variable, and m equals m1 and m equals m2 both satisfy this equation, and hence we have two distinct real roots of this quadratic, and therefore the discriminant of this quadratic must be strictly positive. So therefore the discriminant, which is this expression, is positive, but that implies this is positive. And that settles the proposition, at least in this direction. For the reverse direction, what one has to do is start with this and prove that the algebraic expression, which is ax squared plus 2hxy plus by squared, is the, equal to 0, is the equation of a pair of two distinct straight lines passing through the origin. But since you have this, what you get is that this quadratic has two distinct real roots, call it m1 and m2. And then what you would get is, two distinct real roots. So both of those, if m1 is a root, then y equals m1x would satisfy this algebraic expression, and similarly for y equals m2x, and hence you get two distinct straight lines captured by that algebraic expression. Okay, so so I think that should be clear. And now let us make some more remarks. So here is the full version of the previous proposition. Suppose we have three real numbers a, b, and h, and not all are 0. And then again we have this equation. So then this is the equation of a pair of distinct straight lines passing through the origin. If and only if this happens, this is what we just proved. This would be the equation of a single straight line passing through the origin, if this happens. So the above corresponds to two distinct roots of a certain quadratic. This corresponds to repeated roots. And here what happens? This is the equation of the origin only, meaning the 0 set of this expression contains the origin only, if and only if this happens. which corresponds to having imaginary roots of the quadratic. So the proof is the same, but one would have to make 3 cases in the proof. This is one case, this is another case, and this is another case. So this proposition, this full version of the previous proposition, is a small exercise given what we have done. Okay. Now let us get a certain small snippet of a fact, and then we will look at an example to finish this lecture. So suppose we are given this expression again, ax square plus 2hxy plus by square equals 0, and assume that this is a pair of straight lines passing through the origin. We are not assuming distinctness, but at the very least we are assuming that these are 2 or maybe repeated line passing through the origin. It is not only the origin is all I'm trying to say. In other words, we are assuming h square minus ab is at least 0. Assume b is non-zero, meaning this guy is non-zero. Then the product of the slopes of these lines is a by b. So this assumption b non-zero is important because otherwise we won't be able to write this expression. Also, b equals 0 just means that the vertical line is one of the lines expressed by this equation. Because if you substitute y equals 0, what you get is, if you substitute b equals 0, you get this much is 0, which if you take x out, you will see that x equals 0 is a solution to this equation. So if you have a vertical line, then asking for product of the slopes of the 2 lines is kind of meaningless because the slope of the vertical line is infinity. Alright, so this is what we want to show, but this is very easy. Basically, it's just the quadratic equation trick. So let m1 and m2 be the slopes of the 2 lines, and m1 may be equal to m2 if the straight lines are actually equal. Okay, so then again, as we saw in the previous proof, then setting y equals mix in this expression makes it identically 0. Where for both I, when I write mix, it's for both I equals to 1 and I equals to 2. So that is ax square plus 2h mix square plus bmi square x square is 0, kind of repeating this step from the previous proof. So this implies cutting one step short equal to 0. So this means that, again, this is for both I equals 1 and 2. So that is m1 and m2 are the 2 roots, possibly repeated, are the 2 roots of the quadratic a plus 2h m plus bm square equals 0. Right, but recall what is the product of the roots of a quadratic. The product of the roots of a quadratic, whoops, what have I done? The product of, sorry about this. Yeah, the product of the 2 roots of a quadratic are the coefficient of x to the power 0 divided by the coefficient of x square. Or in our case, it's m. We are not using the variable x, we are using the variable m. So a by b is the product of the 2 roots. And what are the 2 roots? The 2 roots are precisely the slopes of the lines, right? M1 and M2 are the slopes of the line, so that finishes the proof. So the product is a by b, and we are done. Note that the assumption that b non-zero also appears in the course of this argument, because for this to be a quadratic equation, b has to be non-zero, otherwise this is not a quadratic. Okay, so this finishes this proof of a very nice fact. Similarly, we have a formula for the sum of the slopes. So let me just read it out. So what we have is, again, we have the pair of straight lines, and assume b is non-zero, so that the sum of slopes makes sense. If b is 0, then one of the lines is vertical, and then the sum of slopes doesn't make sense. So what we are saying is that the sum of slopes is minus 2h by b. Well, if you include the case b is equal to 0, and with the convention that 1 upon 0 is infinite and infinity plus any real number is infinite, this would be infinite, and it's not like we have to exclude that case out, but let's not push things. Okay, so it's the exact same proof. You make the corresponding quadratic, divide by b in this expression, and just use the formula for the sum of the roots of a quadratic. You get this expression. Okay, and we can put all this together to find the angle between the two lines. So let's say theta be one of the angles, not alpha. Let's use theta. So let theta be one of the angles between the two lines expressed by this equation. Let's say this one is theta. Doesn't matter. So what we are saying is that the tangent of theta in the absolute value is equal to this expression. So what we are finding is, we couldn't have said that tan theta is equal to this expression, because theta is a bit ambiguous. Theta is either this or that. So the best we can say is in the absolute value. It's either, or you could say tan theta is either this with the positive sign or this with the negative sign, depending on whether you're talking about this angle or the other one. There are two angles involved. Okay, so this is the expression. Right, so let's prove it. And the proof we will give will be assuming this, because we will be using the two formulas that we just proved, the formula for the product of slopes and the formula for the sum of slopes. But the expression remains unchanged. You can easily do away with the case when b is non-zero. So if b is 0, then you can easily prove this. So this is true no matter the value of b. Of course, we are assuming that this is a pair of distinct pair of straight lines. So we are assuming that much. Okay. So we'll just use the formula for the tangent of the angle between two lines. Suppose this line has slope m1. Let's say this has slope m1 and this has slope m1 and that has slope m2. Then we know that tan theta in the absolute value is this expression. Right? This is from the very early lectures. So what we can write the expression for m1 and m2, the product of m1 and m2 in terms of these coefficients, because this is the product of slopes, but we don't know anything about this one. We know an expression for the sum of slopes, not the difference. But then there is this simple trick. We square both the sides. So we have tan square theta is this thing, which is equal to that expression. And now the numerator can be written in this fashion. So all we are doing is just using some basic algebra. This thing is equal to that thing. And now we can use the formula for the sum of the slopes and the product of the slopes and get the desired expression. Just paste them in here. Okay. So that's a very nice thing. We can find the angle between the two lines, or the tangent of the angle between the two lines. It's the same thing. And lastly, let's look at a very nice example to finish this lecture off. It will feature a homogenization technique, which is worth learning for its own sake. Okay, so let's get right on with it. So what we want to show is the following. We have this curve which looks like this. It's a hyperbola, but we don't need to know anything about hyperbolas for this problem. So we have this curve, and we want to show that suppose you take a chord of this curve. So what is a chord of this curve? You take two distinct points on this curve and join them via a line segment. That is called the chord of this curve. So amongst all the chords, some of the chords will subtend an angle of 90 degrees at the origin. What does that mean? So suppose you take 2 points. Let's say this point and that point on this curve, and then join them with the origin and find out this angle. This angle. If this is 90 degrees, we say that this chord subtends an angle of 90 degrees at the origin. Okay, so amongst all the chords which subtend 90 degrees at the origin, we want to show that, well, I shouldn't say amongst all the chords, we want to show that all the chords which subtend 90 degrees at the origin pass through a common point. So suppose we have 2 points such that this chord subtends 90 degrees at the origin, then all such chords will pass through a common point. And when I say chords passing through a common point, let me just mean the line spanned by the chord pass through the common point, because a chord is just a finite line segment. A line is a full thing. So all the lines spanned by those chords which subtend an angle 90 degrees at the origin pass through a common point. All of these lines are concurrent, in other words. It's a very interesting problem, and the solution, as far as I'm concerned, is non-trivial. It's not easy. The main idea in this solution is a fairly clever one. So let's now get started with it. So yeah. Okay. So pick 2 points which, let me call these points P and Q. So this is a point P and this is a point Q. And let P and Q be on the curve. And let's call this curve capital H. So be on H such that the chord PQ subtends 90 degrees at the origin. Okay. And let's say this line that passes through P and Q has equation y equals mx plus c. Alright. And since P and Q subtend 90 degrees at the origin, you should be able to see that this line y equals mx plus c, or the line passing through both P and Q, cannot pass through the origin. So let me call this line L, and I'll just write the statement down and you can justify it. Note that L does not pass through the origin.
No,
So therefore C is non-zero. Right? C is this thing. This thing is C, and since this line does not pass through the origin, C is non-zero. Okay. And now here is the kind of the main idea of the proof. Consider these 2 lines. This is one of the lines. The line passing through P and the origin. Right? And then there's this other line. The line passing through Q and the origin. Yeah. Now, the fact that the chord PQ subtends an angle of 90 degrees at the origin is same as saying that these 2 orange lines, this line and that line, they are at an angle of 90 degrees. That's what it means to say that this chord subtends an angle of 90 degrees at the origin. Alright, so the point is that we will be able to write down the equation of this pair of lines. We will write down the equation of this pair of lines, and then we will take the product of the slopes of these two lines and equate it to -1, because two lines being perpendicular is same as saying that their product of slopes is -1, as long as none of the lines are vertical. Okay, so the clever idea is that how do we write down the equation of this pair of straight lines? And to do that, I will directly write down the expression and then justify why indeed that is the required expression. So consider this equation. This thing multiplied with y minus mx divided by c. This equals 0. So this is some curve. This is some algebraic expression equated to 0. So this is some curve, meaning its 0 set is something. Now, note that whatever this curve is, this passes through the point P. Why? Because the coordinates of the point P, when you substitute here, so let's say P is a comma b, then b must be equal to ma plus c, right? Because the point P also lies on this line, and this line is y equals mx plus c. So if P is equal to a comma b, we have b must be equal to ma plus c. And therefore, b minus ma divided by c equals 1. It is legitimate to divide by c because c is non-zero. Alright, so in this expression, if you substitute the coordinates of P, this much becomes 1. And therefore, the remaining part, whatever remains, is basically asking, or whatever remains is, literally what remains is this, 3b square minus a square minus 2a plus 4b. That is what remains, because that much becomes 1. And this is 0 simply because a comma b is lying on the curve h. A comma b are the coordinates of P, and P lies on the curve h. So that's the reason why this thing becomes 0 when you substitute the coordinates of P in it. And hence, this curve contains the point P. And similarly, this curve contains the point Q also. The same reasoning applies. So this is an observation which we gave in words. So let me just write it down. Note that P and Q lie on this curve. Which when I say this curve, this means that curve. Okay, they lie on that line. And now if we just rearrange this, if we just rearrange that thing, what we get is, I have kind of pre-computed it. So you get 3c plus 2m times x square plus twice of minus 2m minus 1 xy plus 4 minus cy square equals 0. That is that curve, because all we have done is just to rearrange things and cross multiply and whatnot. But what did we see? This kind of curve, this is of this form, ax square plus 2hxy plus by square. That is the form of this curve, and hence either this is a pair of distinct straight lines passing through the origin, or just a single straight line passing through the origin, or it is only the origin. It's one of the three. But since this thing already passes through 2 points outside the origin, away from the origin, this cannot be only the origin. It already passes through the point P and the point Q. So this is not only the origin, this is a pair of straight lines passing through the origin, possibly repeated, but it's also not repeated under the assumption that P and Q subtend an angle of 90 degrees at the origin. So it is actually a pair of two distinct straight lines passing through the origin. Doesn't matter. We know since this chord subtends an angle of 90 degrees at the origin, these two lines are perpendicular. So the lines that this curve is capturing are perpendicular, and hence the product of their slopes is -1. And therefore this times that, or rather, sorry, this divided by that is equal to -1, because that is the expression for the product of the slopes. So therefore 3c plus 2m divided by 4 minus c is equal to -1, which implies 3c plus 2m plus 4 minus c is equal to 0, which implies 2c plus m plus 4 is 0, which is giving us something incorrect. That is not what we are supposed to get. Just let me see, maybe I made some mistake somewhere. No, this is fine. 2c plus, sorry, yeah, this is 2m, that is what. So we get c plus m plus 2 is 0. And if we write it this way, we get -2 is equal to m plus c. So just focus on this part, this deduction. Okay, so we had this line y equals mx plus c, and we ended up concluding that -2 equals m plus c. And therefore the point 1 comma -2, this point lies on this line. Because if you substitute 1 comma -2 here, what you get is -2 equals, if you substitute 1 and -2 in place of x and y in this expression, y minus mx plus c, you get that this is 0 because of this equation. Okay, so howsoever you justify it, this just implies that this line passes through the point 1 comma -2. And this is true for any line which, all that we assumed was that these 2 points subtend an angle of 90 degrees at the origin. So all the lines which are of this form, which, such that the corresponding chord subtends an angle of 90 degrees at the origin, will pass through the point 1 comma -2, and we have proven what we wanted to prove. In fact, we have found that point, not just that they pass through a common point. We have found the point. It's 1 comma -2. Okay, a pretty interesting proof, and this was the crucial step, that this, this idea that this way you create the pair of straight lines passing through the points P and Q, that was the crucial step. Okay, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.